Okay, and the sound is good? Online as well? It seems very loud. Is it okay for you guys here? Okay. Okay, we'll keep it then. It's good online, yeah?
I'm checking.
Okay, I heard you.
Yeah.
Okay, let's start in, let's say, half a minute. Looks like Fridays are not the most popular days to come to school. Is that true for other classes also? Yeah, pretty much. Even though the weather is terrible outside, people still prefer not to come to school. Okay, it's fine. I think we can get started. Everything is working. So today we're going to continue on the path we started on branch prediction. As I mentioned, this is a necessary part of a modern processor to work correctly. Well, not correctly, to work at high performance. And we're going to cover a lot of algorithms to make this better. I call this advanced, but we're going to cover some of the basic techniques as well. You've already seen some basic techniques. Just to jog your memory, we're here. We're almost done with all of this, multiple weeks. So by the end of today, you'll be experts in microarchitecture, hopefully. Well, at least you get started on becoming an expert, right? There's a lot it takes to be an expert, of course. There's more you need to learn. Readings, okay, so this is what we were discussing. Basically, there are actually multiple ways of handling control dependencies, just like multiple ways of handling data dependencies. And we talked about some of them, and we were focusing on the branch prediction way, let's say, guessing the next fetch address. And we motivated the importance of this by looking at the slide. Basically, we said that if you have 60% branch prediction accuracy, which is better than random chance, it's terrible for performance in a machine that's not even very aggressive, as you see over here. If you have 90% accuracy, it's still not good, basically. You lose significant amount of performance. You're not able to finish 5 instructions per cycle. You can do up to 1.6 bar instructions per cycle. So 90% is a very good number, as we will see. And this is what we have looked at yesterday. This is the fetch stage with a branch target buffer and a direction predictor. So we are focusing on conditional branches that basically can take the next sequential instruction or the target. You can go to 2 different paths, 2 different next program counters, basically. So I can predict the direction, whether the conditional branch will be taken or not taken. And if it's taken, the branch, if it's predicted to be taken at the beginning of the pipeline, the branch target buffer can supply a target address so that you don't need to calculate it, basically, because it was calculated in a previous execution of this branch. So you store it in this buffer. So this is the fetch engine we have in modern machines in a simplified manner. Modern machines all have this sort of architecture. Okay? And we were focusing on basically how to do this direction prediction, because we said that target prediction is easy for conditional branches where target address is calculated as PC plus offset, because it doesn't change across executions. And this was basically one of the slides that we looked at. We were looking at compile time static branch prediction mechanisms, and we're going to look at more sophisticated mechanisms as well. Remember this slide yesterday? Always not taken means that you predict a conditional branch to be not taken, right? It doesn't matter what the conditional branch is. It's always predicted to be not taken. If your prediction is wrong, you will resolve the branch at the execution stage, and you will flush the instructions in the pipeline, and you will actually predict from start the pipeline from the taken path. So you always correct the prediction, of course, right? And we said that this is not good, but you could actually lay out the code in a different way to try to make it better. Usually these are tough things to do, essentially. Even though they're employed in compilers, it's tough to get very high accuracy. Always taken is slightly better, but again, these are static mechanisms, and we talked about backward taken, forward not taken being slightly better. And then this is the last slide we covered yesterday. Basically, why not distinguish between different branches by having a single bit associated with each branch instruction that indicates a hint as to whether the branch should be predicted as taken or not taken. And this bit can be set by the compiler using profiling, or the programmer if you're doing assembly programming, for example. And this is nice because Now you can do branch prediction on a per conditional branch basis. You can distinguish if one branch is biased to be taken, the hint bit can indicate taken. If another branch is biased to be not taken, the hint bit for that branch can indicate not taken. So it's good. But of course, there are downsides, like it requires changes to the ISA, instruction set architecture right now. And we saw that the accuracy depends on dynamic branch behavior. If the branch is not biased, this doesn't work very well, basically. And you can see two not biased type of branches over here. Basically, I mentioned that I'm going to demonstrate the execution history of a branch using taken and not taken, T and N characters. And you can see that this is 20 different instances of the same branch. In the first 10 instances, the branch is taken. In the second 10 instances, the branch is not taken. So you get essentially 50% accuracy if this is your execution, regardless of how you encode that hint bit, right? If you could encode it as taken or not taken, it doesn't matter. It's 50%. Now that's true for this branch with this dynamic execution behavior. Every instance is the opposite of the prior instance, basically. Taken, not taken, taken, not taken. Again, you get 50% accuracy. And if you look at this, is reasonably predictable behavior, right? But this sort of mechanism doesn't work. Isn't able to capture that predictability. And we also said that if you're actually profiling your program and trying to determine the direction of a branch, your profile input set should better be representative. Meaning, whenever you profile your program and you decide, oh, this branch is taken 90% of the time, you'd better be correct. Because if you're incorrect, and if the branch is actually taken 10% of the time, then you would be making the wrong decision 90% of the time, right? So this example at the bottom demonstrates that. For example, this branch dynamic behavior is 18 instances are taken, and then 2 instances at the end are not taken. If you encoded the hint bit as taken, you get 90% accuracy. If you encoded the hint bit as not taken, you get 10% accuracy. So very much depend on the profile input set. So setting that bit is very important, as you can see. And unfortunately, this behavior with whenever you run a program, for example, with one input, you get this sort of behavior. Whenever you run the same program with some other input, you may get the exact opposite behavior for this branch, right? So that's one problem with the static schemes. They're not able to adapt to the dynamic changes in the program, right? So for example, you may have a branch in your video encoder, and your video may be very smooth, that the branch is always taken. If your video is actually not complex, let's say, it's just basically your video, you're looking at this, and this is very uniform, right? And that branch is maybe always taken in that case, right? Because it's looking at some characteristics of the frame. But if your video is like pointing to you, for example, there's a lot of complexity in the scene, and that same branch that's processing the video may actually have opposite behavior. It may be not taken many times, right? So you can see that's the input set, basically. I just concocted a video processing application with 2 different inputs, this or you, let's say. Okay, so that's important. But we're going to tackle that issue when we move to dynamic branch prediction. Still, static branch prediction is still interesting because people have proposed a lot of mechanisms, but in general, it's not going to work very well, as we will see. But there are interesting ideas. This is an interesting idea that was proposed in this paper. I like the title of this paper, Branch Prediction for Free. And these folks basically said that, look, we don't need to do sophisticated profiling. We can just do program analysis. You have a compiler, and the compiler analyzes the program and uses heuristics based on what it finds out to determine statically predicted direction. We will still have a hint bit for each branch, but the way we're going to set the hint bit is going to be based on some heuristics based on what we understand about the program. For example, if you have a branch less than or equal to 0, these folks say that you should predict that branch not taken, because usually these branches compare an integer value to 0, and negative integers are usually used as error values in programs, and usually those branches are not taken. Of course, it's a heuristic. It doesn't always work, but that's what these folks found out by analyzing the program. This doesn't require any profiling, as you can see, right? The arrival at this heuristic may require some profiling of the programs, but the use of this heuristic on a program doesn't require profiling the program, because you look at the encoding of the branch, it's branch less than or equal to 0. Okay, I'm going to set the hint bit as not taken. Very simple. Not expensive from a compiler perspective. Another heuristic is if you have a branch that's guarding a loop. For example, if some condition, there's a loop, execute the loop. Otherwise, get out, don't execute the loop. These folks say that Usually branches execute the loop because programs are loop-based, so you'd better predict that branch has taken. And the reasoning is, again, somewhat similar to the prior heuristic. If this is a loop guarding branch, it's basically deciding whether or not to execute the loop. There might be some exceptional condition that doesn't execute the loop, but usually the loop is executed. Okay, so interesting. And then they also look at some things like if you compare 2 pointers, for example, predict that they're not going to be equal, usually. And you can imagine that when you're doing a linked list traversal, searching for a key in a key value store, for example, probably you're not going to match most of the time until you get to the point, until you get to the thing that you're searching for, right? If your input data set is large, you're going to match in only one place, basically, out of n places you examine. So there are reasoning behind these heuristics, as you can see. If you're comparing 2 floating point values, which you should not do in your programs in general, because floating point is an inexact representation to begin with, right? Predict not equal. But the pointer is a more realistic use case, if you will. Hopefully this is clear. So these are nice heuristics. They work when they work, but they don't tackle the very hard branches, as you can see, right? Very hard branches are usually that video that I mentioned, right? That's dependent on the input. How are you going to use a heuristics to decide that? Maybe you need a very different heuristic, but it's very difficult to come up with that. So basically, the advantage of this is it doesn't require profiling, which is good. But heuristics might not be representative or good, or may not even be applicable in certain cases where we have very difficult branches to predict. And still, it requires some sort of analysis, cheaper than the profile-based mechanisms. And it still requires ISA support to encode that bit, basically. Okay, so if you're interested, you can read this paper. And these folks show that they can get to 20% misprediction rate, like 80% accuracy, which is not bad in some relatively simple programs of the time. This is 1990s. Today, we're in a different world where programs are much bigger, much larger. They're a lot more data intensive. So branches are actually much more difficult to predict compared to 30 years ago. Okay, but I want to cover this because it's an interesting idea, let's say. Okay, another method is programmer-based. Programmer can also decide what is the likely direction of a branch and hint that to the hardware. And that's the idea, basically. Programmer somehow decides a statically predicted direction. And they do that using pragmas in the programming language. This requires some programming language support. And this pragma should specify whether the branch is likely taken or likely not taken. I'll give you an example soon. But this doesn't require profiling or program analysis, clearly. The programmer needs to do this. And programmer may know some branches that their program behavior, their own program and their potential behavior better than other analysis techniques if they know what they're doing, right? But they may not also know if it's data dependent, right? Because programmer doesn't know which input will be fed to the program as well. So the downside of this is it requires support across the stack, including programming language and the compiler and the ISA. So this is actually an interesting technique. And perhaps other big downside is burdens the programmer. So average programmer doesn't want to deal with this clearly, but even expert programmers may not have time to deal with this also. So let's take a look at these pragmas. The pragmas are actually more general than branch prediction. Have you been exposed to the concept of pragmas in some other course? No, okay, maybe you'll get exposed to it in later. But these are basically keywords in your programming language that a programmer can use to convey information to the lower levels of the hierarchy. Compiler, for example, the operating system, or the hardware, as we will see in this particular case. So they could be seen as hints, if you will. So let's take a look at one keyword. So this C, for example, C programming language has this keyword likely. And if you do this, if likely X, you're hinting that this X is likely true, basically. So this is basically a hint saying that this branch is likely to be taken. Right? Another example is unlikely keyword. If unlikely error, if you do this in your program, the programming language will catch that, oh, this branch is unlikely to be taken, and it will be compiled down to that bit and code in that branch to be set to not taken. Makes sense, right? So these are example pragmas to support branch prediction. And there are many other hints and optimizations that can be enabled with pragmas. Since you haven't seen this, maybe you're not familiar with this, but whether or not a loop can be parallelized can be hinted by the programmer using a pragma. And this is actually very commonly used. If you use OpenMP programming to parallelize your code, there's a pragma called OMP parallel. And this is a description directly from the OpenMP manual. That's a parallelization library to parallelize your code across many computers. Basically, they say the OMP parallel directive explicitly instructs the compiler to parallelize the chosen segment of code, because the programmer knows something about it, saying that it's parallelizable. Of course, the compiler may disagree, right, in the end. That's true for this case also. These are hints. The compiler, in the end, may disagree with the programmer. If they basically somehow have some profiling mechanism, they say, okay, programmer says likely, but I don't think it's likely. That's always the downside with this sort of hints that get supplied at the top. And they may not be obeyed, or they may be dropped at the end, right? These are different from the instructions that you have in the programming language that have to be obeyed, if you will, for the semantic correctness. These are not necessarily necessary for semantic correctness of the program, right? If you mispredict a branch, it doesn't affect your semantic correctness. It may affect your performance, clearly. Okay. So basically, we've covered static branch prediction techniques, and clearly all of these previous techniques can be combined. You can have a compiler that's profiling the program. You can have a compiler that's analyzing the program and using heuristics, and you can have a programmer that's also providing hints. And you can have all of those combined, and then the key is basically figuring out what the branch direction should be, what that hint bit should be. And not so easy, basically, to decide if this information disagrees with each other. But I'm not going to go into how you combine that, because these techniques have a common disadvantage, which we already discussed, which is that they cannot adapt to dynamic changes in branch behavior. Basically, they can encode a single bit, or taken or not taken, for a given branch. If a branch basically switches between taken or not taken in some predictable or regular or irregular ways, you cannot encode that information. So that's why dynamic branch prediction is important. So you can mitigate this. You can mitigate this problem with a dynamic compiler, meaning a compiler once in a while recompiles the program, right? And this actually exists. We've seen it. We're going to see that picture again. But once in a while, you can recompile the program and reset the hint bits, also optimize your code. Unfortunately, there's overhead involved in this. And if you actually do it very frequently, the overhead increases. And usually people don't do it very frequently. But if you can imagine a branch at every execution, it can change its behavior, right? We've already seen it: taken, not taken, taken, not taken, taken, not taken, taken, not taken. How are you going to capture that with a dynamic compiler? Unfortunately, it doesn't work. Well, it could work potentially, but you have to have extremely high overheads to detect that. So what's a dynamic compiler? Basically, a compiler that generates code at runtime, runs once in a while. Java, just-in-time compiler, Microsoft Common Language Runtime. More modern versions, this thing is actually a dynamic binary translator. It can basically figure out the hot parts of the code. And we've also seen the dynamic code optimizer employed by NVIDIA as well. And they actually talk about it. They basically say once in a while, you recompile the code and you figure out which branches are hot, let's say biased or not biased. And I'm sure they encode actually, they talk about it. They encode which branches are biased and not biased, and they make the processing of biased branches easier that way by helping with branch prediction. Okay, so now we're going to jump into dynamic mechanisms that are truly dynamic without requiring a compiler. These are all hardware-based mechanisms. And hardware has the advantage that it has fine-grained information to every single decision that's made by the hardware, right? At a very fast latency, if you will. Because when you make a decision that this branch is taken or not taken, you know that immediately. Right? Whereas communicating that information to a dynamic compiler actually requires buffering it and some software actually reading it after some point. Any questions before we jump into this? We're going to cover a fascinating set of techniques, I think. In the end, we're going to end up with machine learning and also complicated tables, let's say. Some of this may look like, let's say, what should I say, black art, but it's not. Basically, there's a lot of empirical evidence as to why they work, and I'm going to motivate the reasoning why some of these, why all of these work actually. Okay, let's start with basically what's the idea of dynamic branch prediction? Predict the branches based on dynamic information collected at runtime by hardware going forward. So the big advantage is you can basically have a prediction based on the history of the execution of every single branch. That's good. Which enables that you can adapt to dynamic changes in branch behavior. You can easily distinguish taken, not taken patterns. Not initially with the earlier techniques, but we're going to distinguish between them. And there's no need for static profiling, so input set representativeness goes away. That's another advantage of hardware. Hardware is really executing the program as the input set is supplied. You don't need to profile it earlier or during runtime. But of course, this comes with a disadvantage, like everything else. It's more complex, right? This requires additional hardware, and we're going to increasingly add more hardware. And I'm going to show you a picture of one of the Intel processors that has a branch prediction unit that occupies a significant fraction of the computation core. In the grand scheme of things, it's still small, but a sophisticated part of the machine. In the grand scheme of things, everything is memory. Okay, so we're going to start with a very simple idea, last time predictor. Basically, do what you did last time. Like you guys are employing this mechanism. Most people are sitting where they're sitting last time, right? For how many of you is it true? Okay, not bad. For how many of you is it not true? Okay, so it's not a very good prediction mechanism, maybe. For how many of you it's true if you actually coarsen the granularity at which we look at the location, meaning you're kind of in the same vicinity? Okay, that's more hands. For how many of you is it still not true if you coarsen the granularity? Okay, so coarsening the granularity helps, as you can see, right? Okay, good. Basically, last time this is basically what I think you got the idea. Guess that the branch will take the same direction as it took the last instance of execution. Now, this requires a single bit to be recorded per branch. It could be stored in the BTB also, as we will see. And this indicates which direction the branch went last time it was executed. Right? And it works nicely for this pattern, for example. You remember this pattern where the static branch prediction got 50% accuracy. Now we get 90% accuracy. Why? Basically, we mispredict the branch only when it changes the direction compared to the last time. So the branch in the first 10 instances is taken. So you predict in the steady state, you predict 9 of these correctly, except for the last one, beginning one over here. So when you switch direction over here, taken to not taken, you mispredict this instance. You should really predict as not taken the next instance, but you predicted taken because the last instance was taken. And then we're assuming that we're looping in this branch. Basically, the branch shows this behavior, taken, and then not taken 10 times each. So whenever you switch from not taken to taken over here, you mispredict this instance also. Okay. So if you execute this branch in the steady state, you will get 90% accuracy. Makes sense, hopefully, right? Basically, in other ways of putting it, this always mispredicts the last iteration and the first iteration of a loop branch, if you will. This is not necessarily a loop branch, but if you think about a loop branch is taken if you if you keep iterating in the loop, and not taken if you get out of the loop. And if you basically enter this loop many times, whenever you exit the loop, you mispredict the branch. And whenever you execute the loop for the first iteration, you mispredict the branch also, because the last time you executed this branch, you exited the loop. But you should really iterate inside the loop. In other words, accuracy for a loop with k iteration is k minus 2 divided by k. Now, this is not bad if k is very large, clearly, right? So this is actually, if as k goes to infinity, this value gets close to 100%. Right? Unfortunately, as k goes closer to 0, you get closer to 0%, basically, which is worse than static prediction, right? So this is not ideal, as you can see. So you hope that this sort of branches don't exist, but unfortunately they do. So how do we predict them? We're going to see some method of doing that. I mean, you can of course do pattern matching, but we're not going to get to the very sophisticated hardware-intensive method. So this is actually not bad with single bit per branch, as you can see, right? That single bit is dynamically determined. But we're going to fix this 0% accuracy problem. So how do you implement this? Essentially, you index this direction predictor with your program counter whenever you fetch the branch. And this table encodes whether the branch was taken last time, whether the branch at that program counter was taken last time. And you keep updating it based on the outcome of the branch whenever it's executed. Okay? So as I said, this could be actually incorporated into the BTB. You could basically take this direction predictor and incorporate it inside the BTB, because BTB is also indexed with the program counter, right? Why not? Whenever you index the BTB, get the target as well as what happened to the branch last time. And this is one example of this, basically. This is a little bit more detailed. This is your program counter. You use some part of your program counter as index into the BTB. This is a SRAM array or some memory, essentially. We'll see memory more in the future. But essentially, you're indexing a memory, and 1 bit per entry is added to indicate whether the branch was taken last time. And also, you have a 1 target address per entry. Now, you need to make sure, of course, whenever you index the structure, you have a tag. We will see the structure of a cache later on. This is just kind of a foreshadowing. You don't need to understand everything over here. But this is essentially the structure of a cache, as we will see in a couple of lectures. For now, you just need to know that whenever I index my BTB, branch target buffer, with a program counter, I get 1 bit indicating whether that branch was taken last time it was executed and the target address of the branch. Okay. Okay, so you can actually, this is actually a state machine, right? If you look at from the perspective of that bit that encodes whether the branch is taken or not taken, or should be predicted taken as not taken, you have a state machine that goes back and forth between 2 states. Whether if the bit is encoded as 1, you predict the branch as taken. Otherwise, you predict it as not taken. Right? If the branch is actually taken, you stay in that state, predict taken state. When it's resolved, of course. If you predicted the branch taken, but the branch is actually not taken in this instance, you go to this state. So in the next instance, you're going to predict it as not taken. And if the branch was actually not taken and you predict it as not taken, you stay in the state. And you change your decision. If you predicted the branch not taken, and if the branch was actually taken, you change your decision. Basically, if you look at the state machine, one opposing outcome immediately changes your decision. But maybe this is not what we should do with branches, and people have figured this out. And that brings us to the next thing. Basically, one issue with the last time predictor, you could actually come up with other issues also, but one issue that people have found out is that it changes its mind or prediction from taken to not taken or not taken to taken quickly. It sees one piece of evidence and it says, oh, I'm going to predict the branch the other way around. As a result, it may not do well in cases where the branch may have some reasonably dominant direction, but once in a while it changes behavior. Right? Okay, basically, even though the branch may be mostly taken or mostly not taken. So the solution idea that people have developed over time is to add hysteresis. How many of you know the term hysteresis? Okay, if you're a mechanical engineer, you should know this term, but you guys are not mechanical engineers, but I'm going to explain it. But basically, this is some buffer in decision making to make sure that a single different outcome doesn't change the prediction. I like giving the example of air conditioning. So air conditioning systems usually have hysteresis built into them. So you set the temperature, let's say, to 20 degrees Celsius, and the air conditioning doesn't kick in when there's a buffer. Basically, the air conditioning kicks in when when the temperature is, for example, 21 degrees Celsius. Right? It doesn't kick in at 20 degrees Celsius, and so it doesn't start cooling until it sees that the temperature is actually rising. Right? And it doesn't start heating until it sees that the temperature is actually falling too much. So there's a buffer where you monitor what's happening. For example, between 19 degrees to 21 degrees Celsius, and you make your decision based on what's happening. Is the temperature really increasing or decreasing during multiple measurements? If it changes its mind with a single measurement, the temperature increases. Let's say the temperature is 20.001 degrees. It starts cooling, and the temperature goes down to 19.9999 degrees, and then it starts heating. So it keeps switching between cooling and heating, which is really bad actually for you who may be experiencing this, but also very bad for energy efficiency of the cooling system. So it's essentially the same problem over here. We want to add hysteresis. So what this not changing your mind or not initiating the action until you actually have some more evidence that you should really initiate action is called hysteresis. So basically the idea is very simple in hardware. Instead of having one bit to keep track of what happened last time, use 2 bits to keep track of what happened in multiple last times. So based on more information, decide whether or not you change your mind or the prediction. That's the idea. So now you can have two states. So how do you use 2 bits is a question, of course, but you can have 2 states, each representing taken or not taken, instead of 1 state for each. I'm going to show you the example soon. And this was introduced by the seminal paper by Jim Smith. And immediately after that, people adopted this, and this actually increased the prediction accuracy significantly. So let's take a look at this. Now each branch is associated with a 2-bit counter. We still encode the history of last time, what happened to the branch. But we don't look at history of only the last time, but we also look at the previous last time, okay? So 1 more bit provides hysteresis, and we ensure that a strong prediction does not change with a single different outcome. This is also called bimodal prediction, not a great name. But let's take a look at the state machine over here. Now, with 2 bits, you can encode 4 different states, right? And we're going to assign 2 states to be predicted taken, and 2 states to be predicted not taken. Actually, let me go over here. And so, for example, if you predict the branch as taken, and the branch, and you're in this state, let's call this a weakly taken state. You haven't completely made up your mind that branch is actually being taken a lot. If the branch is actually taken, you go to a predicted taken state that's much strongly taken, which indicates that the last 2 outcomes, or at least the last 2 outcomes, were taken. Okay, so strongly taken means that at least the last 2 outcomes were taken. So don't change your mind with 1 opposing outcome. So you see the branch and the prediction is in this state. You predict the branch as taken. If it's actually taken, you stay in the state because we only have 2-bit counters, right? So that's the notion of saturating arithmetic that I had over here. You have 2-bit counter. So if you're strongly predicting the branch as taken and the branch keeps being taken, you cannot increment the counter because you don't have any counter values. So that's the notion of saturating arithmetic. This arithmetic with maximum and minimum values. In this case, the maximum value is 3, 1, 1, and the minimum value is 0, 0. And incrementing the counter or decrementing the counter at the maximum or minimum values doesn't change the value of the state you're in. Okay. So basically, in order to be able to change your mind, if you're predicting the branch strongly taken, meaning at least 2 prior outcomes were taken for that branch, you need to see 2 opposing behaviors, meaning you predict the branch as taken, but the branch was actually not taken. You can see that exclamation mark over here, that's the not taken. Then you go to a state where the branch is weakly taken. In that state, in the next instance, you still predict the branch as taken. And if the branch is actually not taken, at that point, you change your mind in the predictor and you go to a weakly predicted not taken state, okay? So that's the hysteresis basically. Now, of course, you can say, what if you're in the weakly taken state and the branch is actually a weakly not taken state and the branch is actually taken, and then you're in this state and the branch is actually not taken. So you basically run into the same problem again. To solve that problem, you need to add another bit, right? But adding another bit increases your costs. It also makes you less adaptive to these changes. So there's no perfect way of solving this problem unless you do pattern matching somehow. That may be more costly, but this basically adds 1 more bit of hysteresis. It doesn't mean that it gets rid of all of these ping-ponging behavior where you change your mind quickly, but it gets rid of some of them. Does that make sense? So the key takeaway is you change strong prediction only after 2 consecutive mistakes, not after 1 mistake. Okay, so this can be generalized to 3-bit counters, 4-bit counters, but usually people use 2-bit counters. We will see an example where people use 3-bit counters also. Yes? Okay. Mm-hmm. Okay, I mean, I was just discussing that actually. In modern systems, usually 2-bit counters are used because 3-bit counters are harder to manage and also more expensive, clearly. But we will see an instance with the alpha 21-64, there are 3 bits. But in the end, this is not, of course, it's not perfect, right? Not everybody discloses what they do today. So I can see a case for 3 bits if you actually know what you're doing also, right? So when you have 3 bits, you have 8 possible states, right? How do you allocate those states to taken versus not taken also matters, right? You don't have to allocate them equally, right? In this case, we didn't also have to allocate them equally, but we allocate them equally. But with 8 states, you have a much bigger state space. Okay, so that's 2-bit counter-based prediction. Basically, each branch is associated with a 2-bit counter. It can be stored in BTB again, because we're using the program counter to index. This 1 more bit provides hysteresis, and we already said all of this actually. So let's take a look at, let's examine this. So we actually do better compared to last time prediction, as you can see. These are the same 2 branches. This branch is, well, I'm not sure if this is the same 2 branches, but let's take a look at, actually, before we take a look at, now your accuracy for a loop with k iterations is k minus 1 divided by k. You don't change your mind in one opposing outcome, you change your mind in 2 opposing outcomes. So instead of mispredicting this branch twice, you mispredict it only once, right? Meaning, at this point, whenever you're exiting the branch, in this case, it's a slightly different branch, 19 times it's taken, 1 times it's not taken. This is really a truly loop branch, and if you go back, it may exhibit the same behavior. So in the last instance, when the branch is actually not taken, you predicted it as taken, because it was set to strongly taken after this, clearly, right? So you mispredicted it, but you didn't change your mind. It became weakly taken. So whenever you enter the loop again, you're going to predict the branch as taken, right? So you're not going to make the mistake twice here. You're going to make the mistake once. So you get 95% accuracy on this loop branch. That's not bad, right? Now, this more difficult pattern earlier, where we actually got 0% accuracy with the last time predictor, assuming the counter is initialized to weakly taken, we get 50% accuracy, right? Because if the counter is initialized to weakly taken, we will predict this first instance as taken, so the counter will become strongly taken. And then the next instance will predict as taken, but we'll mispredict it, so the counter will become weakly taken, okay? But we mispredicted it. In the next instance, we'll predict correctly as taken, this counter will become strongly taken again. And then basically the counter will jump between strongly taken and weakly taken, but we will mispredict every other instance of the branch. So 50%, which is not bad, but not that great also, as you can see. So this is where some more sophisticated predictions can help. This is one of the reasons why modern processors actually add loop branches, loop branch predictors that is specialized for loops. Okay, we're going to use other techniques to fix that 50%. So essentially, you get better prediction accuracy with 2-bit counter-based prediction, but more hardware cost. And that's going to be our story for the rest of the lecture also. So the question is this good enough? This was demonstrated to have 80 to 90% accuracy for many programs. But again, landscape has changed today. We have actually much more sophisticated programs today. I don't think this has been tested with those programs today. And is this good enough? And you know the answer, right? So I give you this picture that I kind of showed last time. 80% accuracy, you fetch 400% extra instructions with these assumptions, and your IPC is 1 as opposed to 5, which is ideal. Okay, you say 85%, still not good. You say 90%, still not good, basically. Basically, it's not good enough. So the question is, can we do better? And this is what people have been asking in branch prediction and everything else we've been covering in this course. So we're going to do better. And the idea that actually really leapfrogged the processors at the time was introduced by this paper. And the idea is called 2-level prediction. So instead of looking at 1 level of history, look at 2 levels of history. That's the idea. Now, what does this mean, of course? Let's take a look at what this means. So we exploited, with these predictors earlier, we really exploit last time predictability of the branch. What happened to the branch in the last instance or last n instances if you're using multiple bits to encode the last prediction? So people have realized that, oh, there's another level of predictability in branches, meaning if one branch's outcome can be correlated with other branches' outcomes. Not just this branch, what happened to this branch last time, but what happened to branch A, B, C in the program, and they're somehow correlated to each other. I'm going to motivate this. And this is called global branch correlation. And we're going to design global branch predictors. And people also realize that a branch's outcome can be correlated with past outcomes of the same branch, other than the outcome of the branch last time it was executed. So you look at a bigger pattern of history of what happened to this branch, and that gives you the prediction currently. And that will fix the problem with this second. Basically here, if you look at the longer pattern, if you, for example, say, if you look at 4-bit of history, taken, not taken, taken, not taken, the next prediction is obviously not taken, right? Whereas if the history was not taken, taken, not taken, taken, the obvious next prediction is not taken. So you can actually learn that history. But we're not exploiting that history over here. So that's what we need to do. Well, people have done. And you can actually build relatively simple hardware for this. So let's start with the first realization. First realization, I think, is fascinating because it's amazing that people did not come up with that realization for 10 years until after since that 2-bit counter prediction paper. But basically, the realization is that recently executed branch outcomes and the execution path are correlated with the outcome of the next branch. And these may be different branches. We're thinking about different branches, but it can be the same branch also, actually. The mechanism that we're going to look at is not going to distinguish between which branch it is. For example, let's take a look at this code. The first branch is testing condition 1. The second branch is testing condition 1 and condition 2. Now, if the first branch is not taken, you can be sure that the second branch is also not taken. Right? So it's clear there's a correlation between these branches. So that's good. So if I predict this not taken, and if I'm correct, I'd better predict this not taken also, right? Otherwise, I'm inconsistent with my predictions. And I'm hoping that I'm correct in my predictions. Okay, another one. This branch is taking x is less than 1. This branch taking testing x is greater than 1. Clear there's a correlation here. Similarly, this branch is testing. This is a more sophisticated correlation. If condition 1 is true, we set a to 2. And the other branch is testing whether a is equal to 0. So if this branch is taken, this is not taken. That's true for this one also, right? So both of these cases, if the first branch is taken, the second is definitely not taken. So again, whenever you're doing this prediction, you'd better look at this correlation. Now, there are more sophisticated correlations. I'm going to show you another sophisticated correlation soon, but these are two different branches. One is testing condition 1, the other is testing condition 2. And the third one is testing condition 1 and condition 2. If the first two branches are both taken, then the third branch is also taken. If Y or Z, if the first or the second branch is not taken, then the last branch is also not taken. So you can see there's a nice correlation. And if you actually encode what happened to the prior branches, you can get to a better prediction accuracy. This used to be a very tough workload. This is the SPEC, Standard Performance Evaluation Corporation. And a lot of processors were designed to fail, let's say, in this code, until people invented global branch predictor. But if you look at this code, if this branch is taken and this branch is taken, then this branch is not taken because they're setting AA and BB that this branch is testing. Right? And it turned out a lot of processors could not do this well. The prediction accuracy was less than 80%. This was actually interesting because from the perspective of our course, because this generates a truth table from a Boolean expression. It's one of those programs that's used for designing computers, actually. Equation to truth table, equan t tot, I guess, whatever. Equation to truth table. So this can be relatively easily captured with a global branch predictor. Okay, and these are very data dependent, as you can see, right? The branch may change behavior. So how do you capture this? Basically, that's the key idea. That's the key realization of this work. Associate branch outcomes with a global taken, not taken history of all branches. Now, what does this mean? Well, we're going to see that basically. You keep a global history of all branches, which direction the last n branches took. And you encode that as taken, not taken, 1 or 0. You may have a global, this is called a global history register. It could be 4 bits. 4 bits means which directions did the last 4 branches go to? Taken, taken, not taken, taken, for example. Right. Existing processors have 16 bits and even larger, as we will see. But initially, it was 4 bits in Pentium Pro. And then you make a prediction based on the outcome of the branch the last time the same global history was encountered. So you basically correlate the global history that you see with what happened at that global history last time you saw that global history. We're not looking at what happened to the branch last time. We're not using a program counter, actually. We're using the global history to decide what happened last time I saw this global history. Does that make sense? I'm going to show you an example. So this is the implementation, basically. You keep track of the global taken, not taken history of all branches. That's why it's called a global correlation in a register, global history register. No program counters here, okay? And you use this global history register to index into a table that recorded the outcome that was seen for each global history register value in the recent past. This is called a pattern history table. It could be 1 bit again. It could be 2-bit counters to account for hysteresis. Last time I saw this global history, the branch that I'm trying to predict, it doesn't matter what branch it is, I actually had a taken outcome or not taken outcome. Now you can actually have 2-bit history over there also, right? Just like we did for a program counter. Okay, so this is called a global history or global branch predictor. It uses 2 levels of history. One is this global history register, and the second is what happened, the history at that global history register. What happened last time when I saw this global history? Okay, so this is what it looks like basically. This is the global history register. It's essentially a single register which encodes the prior directions of prior branches, the direction of last n branches. It's m bits. As I said, in Pentium Pro, it was 4 bits. In modern processors, it could be much larger. So you use this to index a pattern history table, which has 2 to the n entries, which associates the direction the branch took the last time the same history was seen. Okay? So if you saw 1111110, you index to that location. What happened to the branch at the, when I saw this history last time? Again, I'm not distinguishing between different branches. What happened to this? What happened to whatever branch I'm fetching right now? Last time I saw this history. Okay? So that's the idea. And this pattern history table can be a single bit, meaning it basically looks at the last time, what happened only in the last instance I saw this history, or it could be a 2-bit counter, which has hysteresis in the last instances of the time I saw this history. Okay? So that's the beauty of this. Any questions? Now let's take a look at what the paper that I assigned you shows. Now this is not the greatest example because these are static values encoded in a loop. You could predict these much easily, but it shows that a global branch predictor works even in this instance. So basically we have these 2 loops, the inner loop, the outer loop. And basically these are the 4 branches that are associated with this. The 3 branches are testing whether j is less than 3 for 3 different iterations of the inner loop. And this is the outer loop. Basically, the paper that I assigned you says, after the initial startup time, the conditional branches have the following behavior. Assuming global history register, it calls the global register, is shifted to the left. So let's take a look at the last instance over here, the outer loop branch. It's testing whether I is less than 100. It's usually taken, actually, as you can see, because, yeah, you exited only in the 100th instance, right? So this branch tests I. Last 3 branches test j. And the history of last 3 branches is actually taken, not taken, right? And the prior branch is actually testing I, so that's taken. So the last 4 branches are really taken, not taken. And whenever you see this history, you'd better predict this as taken, because this is usually taken, right? So you don't need to know which branch it is. You just look at the history, and this history really distinguishes this outer loop branch. Whenever you see this history, that's the outer loop branch in this particular code. So you predicted taken. Now, next history will be taken, not taken, because this branch will be taken. In other words, it's 1101, as you can see. 1101 distinguishes the next branch, which is essentially taken. It's actually always taken in this particular case. So whenever you see 1101, you will always be accurate in this case. And then you shift in the next outcome, shift out the oldest outcome. So it's going to be taken, not taken, 1011. That's also going to be taken always, because that's the next iteration of the inner loop. And you will always be correct on that one also. And then you shift in the this taken outcome and then shift out the oldest outcome. It'll be not taken, 0111. And this is going to be not taken always again, right? Because this is actually static, as you can see. Okay? So you will actually mispredict no branch over here at the steady state, except for the last iteration of the outer loop. Make sense? So it's beautiful, as you can see. And we didn't even distinguish between branches. There's no program counter involved in this. It's just, we're just looking at a 4-bit global history register. So that's the fascinating thing over here. And this is another paper that we're going to discuss that introduced actually, that nicely explains this, even though this is not the perfect example, but it's a kind of nice example. Okay. Okay, so this global branch predictor was implemented in Intel Pentium Pro, and it was actually what made it really successful, I would argue. They had a 2-level global branch predictor, 4-bit global history register, and they had multiple pattern history tables. That was the difference. So instead of having a single pattern history table, they actually had multiple, I believe 4, maybe they didn't disclose it, but they actually tried to separate different program counters also. So they wanted to use different pattern history tables for using 2 bits of the program counter, for example, so that they actually have some program counter information in the predictability also, in addition to the global correlation information. And what made this processor really successful was a combination of all of these. We've already seen out of order execution, superscalar execution, and precise exceptions using a reorder buffer. Now you know the last component, 2-level branch prediction. If they had a last time branch prediction, their performance would not be as good, basically. Okay, and you have seen this picture multiple times. Now let me give you the global branch correlation analysis. Why does it work? I mean, we've already seen why this works, actually. But there's a lot of interesting papers that have been written on this. Like, you're looking at this history, but not all branches actually correlate with this branch, right? There's a lot of noise in this history potentially also, especially if you're looking at longer histories, like 100, I think this paper looks at 512 bits of history, basically, last 512 branches. And this interesting paper shows that only about 3 past branches directions matter in the workloads they examined in the past, of course. So this is going to be the motivation for what we will see later on, a machine learning method that uses perceptron, that essentially uses the global history, but it tries to find actual correlations between the positions in the global history and the branch you're predicting. That's the idea. Can you actually find correlations between the position in the global history and the branch you're predicting, and use really that information or that weight, give higher weight to the really correlated branches with the branch that you're trying to predict. We're not doing that in this simple hardware mechanism that we discussed, right? There's no weight here. You just look at the history. So we're going to do more expensive computation in perceptron branch predictors very soon. And that's really employed in modern processors. AMD Zen 2, for example, employs that. Okay, so let's talk about improving global branch predictor accuracy, and then we're going to take a break before we get to the local one. So people decided that actually this is a very good approach, and they tried to improve its accuracy in many ways. I'm going to give you one idea, which was introduced by this paper. This paper was never published anywhere. It was published by Digital Equipment Corporation as a technical report, but it had a lot of impact. Basically, the idea is to add more context information to the global predictor to take into account which branch is being predicted. Now, notice that Intel Pentium Pro did this actually by separating the pattern history tables based on the program counter information. But there's another way of doing this more cheaply, let's say, and that's the idea of the G-share predictor. You hash the global history register with the branch program counter. This is where black magic kind of comes in. Not black magic, but this is the art of hashing, I would say. Instead of using just a global history register, you also take the branch address or some bits in the branch address, usually the lower bits because there's more entropy over there to distinguish the branches, and then XOR them or use some other hash function. XOR is, of course, simple to compute clearly, right? And then you index the pattern history table to get the 2-bit counter. That's the idea. So why does this work? Why does this work better than the global history register? And this has been proven to work better, actually, empirically, of course. Because you use more context information to use for the prediction. You don't just use the global history, but you add some more information about the branch as well. And this actually helps you distinguish the global history on a per branch basis a little bit. It also enables better utilization of the 2-bit counter array, it turns out. Basically, the same history for a different branch may lead to somewhat different outcomes. But also, it's if you use the same history all the time, you're not utilizing the pattern history table very well. For example, if you have a 16-bit history, you have 2 to the 16 entries in this pattern history table, and some of these locations are not very well utilized. If you use this sort of hashing, it enables better utilization and also a better prediction because you reduce the, let's say, interference that happens if you don't utilize the pattern history table very well. But of course, the downside is now increased access latency slightly. It's not that bad. We'll see much worse techniques that increase access latency, and it clearly adds some more hardware cost. But this is shown to be better. Let me demonstrate this. So this was where we were, right? We used the program counter to index the direction predictor. This was a last time predictor. And then we said, we said, forget about the program. Let me do this. Yeah, we said, forget about the program counter. Program counter is used to get the target address, but we're going to use the global branch history to index the direction predictor. This is a global history predictor. And we're going to use only that. That's the 2-level global history branch predictor. Now, G-share says that don't forget about the program counter. Actually use the program counter and hash it with the global branch history register and then index the direction predictor using the hashed value. Okay? And that actually provides better accuracy. Okay, and this is a very good place to stop. Feel free to collect questions, and we're going to start with the local branch correlation, and then we're going to be more sophisticated after that. Let's be back at 15:20. Sure. Okay, let's get started. Everything is still good online? Okay. Okay, now we're going to move to the second realization, but I should say that global branch correlation has been explored a lot. I will give you a teaser also. I like the idea of agree prediction. Maybe you don't know what that is. There is in the backup slides. But instead of encoding whether or not, encoding taken, not taken history in a pattern history table. So you've seen a global history. You normally we encode whether the branch is taken or not taken, right? Encode a bias bit saying this particular place, this is the bias for this particular thing. And keep track of whether you agree with the bias or disagree with the bias. So if you actually do that, you improve the branch prediction accuracy also. Now, if you wonder why, you have to do the mathematical analysis, and I'll let you do that in the backup slides if you're interested. So people have actually invested a lot of effort into figuring out how to improve the accuracy using, let's say, tricks like this. Okay, so let's come to the second major direction, which is local branch correlation. Local in a bigger sense. Basically, a branch's outcome can be correlated with past outcomes of the same branch, in addition to the outcome of the branch last time it was executed. So basically, you look at the pattern, local history pattern, in a local history register. So let's take a look at what this means. And we've actually seen this earlier with my taken, not taken, taken, not taken example, but this is kind of similar. But if you, this is from your paper that I suggested that you read. If you look at the simple loop, if the loop test is done at the end of the body, the corresponding branch will execute the pattern taken, 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 not taken to the n, where 1 and 0 represent taken and not taken respectively, and n is the number of times the loop is executed. Clearly, if we knew the direction this branch had gone on the previous 3 executions, then we could always be able to predict the next branch direction. Why? Because basically, this is why, essentially. Essentially, the different iterations in that loop, if you use the last 4 bits of what happened to the iterations, last 4 outcomes of this branch, and index into a pattern history table, and record basically what happened, or what should happen to that branch, you can identify the different loop iterations, essentially. For example, if you see these 3, 1, 1, 1, 0, the next prediction should be taken because you're executing the loop again, right? That's the first iteration at the beginning of the loop. If you see these 3, 0, 1, 1, 1, that means that this is the last iteration of the loop, so you'd better predict that as not taken. Right? If you see any other history in between, 1, 1, 0, 1 and 1, 0, 1, 1, that means that you should predict the branch as taken because you're executing the loop. Of course, this is a relatively easy loop. It's statically predicted. It's short, but this is the motivation, basically. You can distinguish between different iterations of the loop, and that way you can actually predict the branch accurately in all instances in this particular case. So that's the idea, basically. In this case, I also say to predict a loop branch perfectly, we want to identify the last iteration of the loop. And this sort of prediction that looks at the local history of the branch identifies all iterations of the loop, actually. Right? So by having a separate pattern history table entry for each local history, we can distinguish different iterations of a loop. Of course, this works for short loops. Now, you can also find some other motivations, but this is the nicest motivation, let's say, from loop branches. So how do you capture this? Essentially, now, instead of having a global history register, we have a per branch history register. That's the idea. And we associate the predicted outcome of a branch with the taken, not taken history of the same branch. That's what this per branch history register does. And then we make a prediction based on the outcome of the branch, the last time the same local branch history was encountered. So previously in the global history register, we had a global history register, and we basically looked at what happened last time I saw this global history, taken or not taken, and then added hysteresis. Here we have a local history. What happened last time I saw this local history for this branch, taken or not taken? So it's very similar. We're going to use another history register and index into a pattern history table, 2-bit counters, and then get that information. In this case, the local history is per branch history, though. So this is called the local history or local branch predictor. Again, it still uses 2 levels of history. First level is the per branch history register, and the second level is the history at that history register value. That second history is taken, not taken, or whatever number of bits that you use to encode hysteresis in the last n outcomes. Okay, so this is again what two-level local branch prediction looks like. Remember, we had only one global history register in the global one. Now we have local history registers, ideally one for each branch. So essentially, in the first level, you have a set of local history registers. Each of them is m bits. And we select the history register based on the program counter of the branch. So we use the program counter to index this and get the local history of what happened to the branch in the last n executions in terms of taken or not taken outcome. That's our local history. And then we use that local history to index a table of saturating counters for each history entry. So if this is n, we have a 2 to the n entry pattern history table. Right. And this is essentially the same function. The direction the branch took the last time, the same history was C. Okay? It may look different, but it's not that different, basically. It's essentially you're using a different history register to index into a pattern history table. Okay? Now, this pattern history table, actually, it makes sense to make it per branch as well in this particular case, so that you can distinguish between different branches. But of course, that amplifies the hardware cost. Right? Okay, so that's our local two-level local branch prediction, basically. And let's take a look at it. Basically, I've shown you the global version of this, and then the G-share version of this. This is what the local version looks like. You take the program counter, there's no global history here, and you index into this table of local history registers. Based on the program counter, you get a local history for that branch, and you use that to index into your direction predictor, which is the pattern history table, as we showed earlier. Now you can see that this increases your critical path a little bit more, right? Because this could be a pretty large table, depending on how large you make it. If you want to distinguish every single branch, it's a huge table, of course. If you want some, if you're okay with some aliasing, of course, this could be smaller. Of course. Okay, so basically, the key realization is that each local history register encodes which directions earlier instances of this branch went. This branch at this program counter. Okay, so this paper introduced a taxonomy of two-level branch predictors. You could actually mix and match things. So you have essentially a branch history register. This branch history register can be global, or it could be for a per set of branches, or it could be per branch. Per branch is very expensive, of course. Per set of branches is basically you take some bits in the program counter and you use that to index. Clearly, some branches will share some bits in the program counter, so there's some aliasing. Pattern history table can be global, meaning there's only one table, or per set of branches, like Pentium Pro did. They use basically some bits in the program counter to index into different pattern history tables. Or it could be per branch, which is clearly very expensive, right? Lots of pattern history tables. And these are 3 examples. This is really the global predictor that's used in Pentium Pro. The branch history register is global. It's called the global history register. And then you have a global pattern history table entries. Okay? This is per address branch history table over here, which is local, essentially, or per set of branches, if you will. But it's still local. And then you have a shared pattern history table. You may question, why does this make sense? Does this not make sense? Well, if you have hardware costs in your mind, this may make sense, right? But logically, this may not make a lot of sense because you're trying to distinguish the local history of the branches and you kind of index into the same table across different branches, right? So logically, this is not necessarily great. And this is the most expensive version per address or per branch local history table. Per branch, per branch, branch history registers. So you have basically a different local history register for each branch. And then each local history register indexed into a separate table. There's no interference between these tables. So this is quite expensive, clearly, and it's not employed in existing processors. But you will see that the other ones are actually employed. Well, we've already seen, actually. Okay, any questions? Okay. So the question is, of course, can we always do better, right? And we're going to see that we can. And we're going to exploit more behavior in the program, especially the predictability of branches. So it turns out some branches are more predictable using local history, and some branches are more predictable using global history. For others, a simple 2-bit counter is enough, yet for others, a single bit is enough, basically. It's very biased. So for example, if you're testing an exceptional condition, you'd better predict that branch as not taken, right? Assuming that the exception will not happen. If it happens, you have a bigger problem at hand. You need to solve the exception, right? So there are some branches that are actually very unlikely to be taken or not taken, essentially. These are extremely biased branches. And in general, it's better to use different mechanisms tailored for different types of branches. Essentially, the observation is that there's a lot of heterogeneity in the predictability behavior of different branches. And there's no one-size-fits-all branch prediction algorithm for all branches. That's why people developed the idea of exploiting this heterogeneity by designing heterogeneity inside the predictor itself. So why don't we design heterogeneous or hybrid branch predictors to customize the predictor for different types of branches? So this is the idea of hybrid branch predictors. And again, the idea is very simple. Use more than one type of predictor. In other words, multiple algorithms to select and then select the best prediction. Now that's going to be difficult, right? Which one's the best prediction, right? So for example, you can have a hybrid of 2-bit counters and a global predictor, right? And then you decide which one provides the best prediction for a given branch, or for a given history, or for a given context in the program. So there's a lot of design choice. Now the design choice actually explodes over here. So let's talk about the advantages. The advantages are actually better accuracy in this case. Different predictors are better for different branches. And if you can identify the best predictor for each branch, you can actually get much better accuracy. There's also another advantage that we did not talk much about, but you get a reduced warm-up time. Meaning some predictors actually takes time to warm them up. Because imagine a global history of, I don't know, 32 bits. You need to see a lot of instances of that history to actually make a decision that, oh, this is going to be taken or not taken in this particular history location, right? What do you do until then? Do you not make a decision, or do you just randomly choose a decision, randomly set the bits in the pattern history table? Both of them could be, well, not making a decision is not good, basically. So there's a warm-up problem, basically, to really warm up, to get the dynamic branch predictor warmed up such that it's trained for the application that's being executed. So if you use a simpler predictable, you can actually use the faster warm-up predictor until the slower warm-up predictor is warmed up, essentially. That's the idea. So this requires, of course, figuring out when things get warmed up. So we're not going to go into that. The disadvantage of this, now you need a meta predictor to select between different predictors. How do you select the best predictor for a given branch? This is also called a selector. You have a longer access latency because you have multiple predictors, and then you have to decide on which one you're going to use. And you have more hardware and complexity, clearly. Now we're making the branch predictor larger and larger and larger. For good reason, as we have discussed, right? Because if we don't have good accuracy, we'll have a problem. So this is employed in modern processors. All modern processors have hybrid branch predictors. Alpha 21-264 was one of the first ones to implement this. And you can see some design choices that they made. So you can see there's a global history predictor, just like we've seen, except they use a 12-bit history over here, 12-bit of global history. And they have 2 to the 12 entry pattern history table entries, and each of them is 2 bits, right? This is the global predictor, this gray part over here. It supplies a prediction for a given branch. And you can see that program counter is not involved over here. This is a purely global predictor. And then there's a local predictor that they use, just like we discussed earlier. They use the program counter to index 10 bits of the program counter to index into a local history table. Each local history table is 10 bits long, so the local history is 10 bits. What happened to this particular branch in the last 10 instances? And then they use those 10 bits to index into the pattern history table through the 10 entries. Each of them is 3 bits, as you can see. So they decided 3 bits was better for local history after probably empirical evaluation. But you can see that this is not per branch because you use 10 bits of the program counter in a hashed way, potentially. They don't talk about that clearly in this figure. But some branches alias go to the same entry. And clearly this local predictor also has a lot of aliasing, assuming this is what they really implemented in hardware, because it tells you what happened to the branch at that local history, but other branches also mapped to this table, right? Okay, so basically this is the local predictor, this is the global predictor, just like we've described. And you get 2 predictions, local prediction and global prediction. And then there's a final prediction. You have to decide which one to use. And that's decided by this choice predictor that they decided. Basically, it uses 12 bits of global history, assuming this picture is accurate again. right? Internally in hardware, they may do something else. But basically, they use the global branch history, global history to track which predictor did better, let's say, last time with some hysteresis when this global history was encountered. Okay? So why do they do that? Because they probably found out that this was better for deciding which predictor to use. Okay? So you can use the same concept to decide which predictor. But in this case, you're not encoding whether the branch is taken or not taken. You're basically encoding which predictor did better, gave the correct outcome for the branch. So that's the decision maker, if you will, or meta predictor. They call it the choice predictor. So alpha was interesting. This is a paper that I assigned optionally. You can see that they claim that the typical branch penalty is 11 plus cycles. That's why actually they built this hybrid branch predictor. And they embedded the BTB inside the iCache, instruction cache. And they have, you can see a large amount of target addresses. And they reset the predictor tables on a context switch. I added this over here because there are other issues that we're not going to discuss. What happens to these tables on a context switch whenever you switch in some other program? Do you use the prediction, like the tables were populated based on the execution of some other program? Do you use that information for the other program, right? It usually doesn't make sense, so they reset the tables. But you could use other things potentially. Okay, so I find this fascinating. It's good that people actually wrote papers about it. Today, people are more secretive, let's say. So security researchers tend to reverse engineer things to figure out what's going on, or architecture researchers as well. So there's another idea that I would like to discuss that relieves the predictor a lot, and this is biased branches and branch filtering. Basically, the observation is what I said earlier. Many branches are biased in one direction. For example, 99% taken or 99% not taken. And these branches are actually easy to predict, but they make your life harder by polluting these structures that we are designing for actually harder to predict branches. So they make the prediction of other branches difficult by causing interference in the table, branch prediction tables and history registers. So the solution is to detect such branches and predict them with a simpler predictor, last time, static, etc. And this was introduced by this work, and a lot of actually existing processors and proposed predictors do this. They try to use as simple as possible predictor to predict a branch accurately. That's the idea. Now, how do you do that? To be able to do that, you need to collect more information about a branch. Right? Which predictor is doing better for this branch? Is it really biased? So I can find out the bias of a branch, for example, by collecting the taken frequency or not taken frequency of a branch while the branch is running. You can have another table that says, oh, in this program counter, I index this for the program counter, and more than 99% of the time this was taken. So I'm not going to use all of the other prediction structures for this particular branch. More hardware, but better accuracy. Okay, any questions? So there are a lot of ideas, as you can see. So are we done with branch prediction? Basically, hybrid branch predictions work well. And 90 to 95% prediction accuracy on average is reported. But again, these are older programs. And I can show you my slide again, but I'll show you a different way. So some difficult workloads, even though they're old programs, still suffer a lot. For example, the GCC is a compiler, GNU compiler. It's very commonly used. For one configuration in this paper that you're actually, I think this is one of the papers that I assigned, the McFarling paper. The maximum instructions per cycle with alpha-like tournament prediction is 9. But if you get perfect prediction, you should go up to 35. This is unlimited resources in the machine. So we're still not there yet, even with 90% or 85% accuracy. So that's why people have been developing a lot of different branch predictors, and we're going to cover some of them. There's a lot more to do in this area, but it's a hard area also. It's not like the memory system where there's a lot of ideas you can explore, which is less explored, but this is an area that's more explored, as you can see. And also you're very limited in terms of what sophistication you can add to the hardware. Like you cannot really add extremely complex algorithms here. That's why the machine learning algorithm that we're going to look at is going to be one of the earliest proposals for machine learning, if you will. Okay, so these are some of the other branch predictor types we're going to examine. Loop branch detector and predictor, this is actually interesting. This tries to detect the iteration counts of a loop. Whenever you get to a loop branch, you detect this as a loop branch with some heuristics. And then you basically try to figure out what the iteration count should be based on past executions. And this is used in Intel processors. Actually, it's used in most processors. Perceptron branch predictor, we're going to look at this. And I kind of foreshadowed it, right? This is a global branch predictor, but it tries to learn the direction correlations between individual branches. And it assigns weights to correlations using simple machine learning, which is perceptron. How many people know about what a perceptron is? Okay, not that many. Okay, so you're going to learn if you haven't learned. So we're going to talk about that. But this is used in AMD's recent processors and maybe other processors that don't disclose what they do. And then we're also going to talk about a competitor to this, which is heuristic-based, not machine learning-based. But it's more accurate, actually, it turns out, given the same hardware cost, which is a hybrid history length branch predictor. It uses different tables with different history lengths for different branches. So if a branch requires a short history length, use a small table. If a branch requires a huge history length, 512 history lengths, because the branch that you're correlated with is far away in the program, maybe outside the loop, use that for that branch and figure out which one is going to work well. And this work actually shows that it makes sense to actually design your tables with a geometric series in terms of history length, so that you can cover a very, very large variety of history lengths, if you will, with low hardware cost. This is also used in the AMZ Zen 2 family. Okay, let's take a look at Intel Pentium M predictors. Actually, for example, this is a very simple loop predictor. Whenever you see a loop branch, you predict how many iterations this loop will execute. That's what the limit is. And then you start counting how many times you see the loop branch. You predict the branch to be taken as long as count is less than the limit. Once count becomes equal to the limit, you predict the branch is not taken. So the question is, of course, there are multiple questions. How do you detect the loop branch? Usually backward branches are loop branches, but not all of them. How do you decide on what the limit should be? That's the difficult part, basically. You can guess. You can use the last time as a limit. You can use a more better view. You can use some hysteresis over here also, but you need to be smarter in terms of how you figure out the hysteresis. So this is the loop branch predictor that's used in this and somewhat explained in this paper. But I should also mention something we're not going to talk about unless we magically have time at the end of this lecture, which I don't expect to happen. But existing processors also have indirect branch predictors. We're talking about conditional branches, but existing processors support indirect branch predictors. Indirect branch predictor is an unconditional branch where the target address is determined by a register value. So it can have actually a very large amount of target addresses. So they have support for indirect branch prediction, and they have separate structures for indirect branch prediction, which I'm not going to talk about further. But there are a lot of ideas that are developed in that domain as well. Okay, so this is Intel Pentium M. If you look at the advanced branch prediction logic that they claim to be here, so it's a reasonably large chunk of the processor core, right? The rest is memory, as you can see. Well, a lot of the regular structures are memory. Okay. Now let's jump into more advanced branch prediction, and we're going to cover these other algorithms that I promised to cover. Let's talk about perceptrons. Since many of you don't know, this was actually developed in late 1950s, and this is when people were actually looking at machine learning, the first iteration, let's say. And this is how they modeled a biological neuron. It's a simplified model of a biological neuron as people understood neurons at the time. It's also a simple binary classifier. Essentially, it can classify things. So essentially, what does it do? Basically, it maps an input vector x to a 1 or 0. That's the classification. Now, what does that mean, essentially? So input is some vector x. Essentially, it's a set of values. And the perceptron learns the linear function, assuming one exists, of how each element of the vector affects the output. Okay? And this is stored in an internal weight vector. Right? There's a weight associated with each element of the vector, and you basically learn how each element affects the output. Whether it will bias the output towards 0 or 1 depends on the weight associated with it. Okay? So output is calculated this way mathematically. Essentially, it's a statistical learning mechanism, just like all machine learning, if you will. But basically, you have output, and output is assigned to a value that looks like this. And the value is calculated as weight multiplied by x. You have a weight vector multiplied by a vector x, so it's a dot product. And then you add a bias that you can also learn. And if this is greater than 0, output is 1, otherwise the output is 0. Makes sense, right? So you could use this for detection, for example, of a language, let's say. You could train it in some way, and each word in a language may have some weight in terms of whether it belongs to this language, right? For example, you have a word, it belongs to German, and it is a very high weight if it's really a German word. If it's a really low weight if it's not a German word, right? If it's not clear, then it may have a somewhat low confidence weight. And then someone gives you a sentence consisting of multiple words, and then you multiply those, you basically parse that sentence into words, and you figure out the weight of each word and do a dot product. And then basically decide whether that sentence belongs to, let's say, a language, German, for example. Hopefully this gives you an intuitive example of what this might represent. Usually language classification is relatively one of the easier tasks, and it could be done somewhat with perceptrons, if you will. Okay, so in the branch prediction context, let's pull our context back to branch prediction. You could actually apply this to many things. It may or may not work very well. But in the branch prediction context, what are our weights, outputs? Basically, vector X is the branch history register bits. Remember the global history register? Each bit is a bit in the vector, essentially. You could treat the global history register as a vector. Output is the prediction for the current branch. Then what are weights? Basically, weights are the correlation between the prediction and each of the bits, essentially. So let's take a look at it in a little bit more detail over here, how this perceptron works. So basically, the high-level idea is to use a perceptron to learn the correlations between branch history register bits and the outcome of the branch, which is ideally our prediction, right? So a perceptron learns a target Boolean function of n inputs, and you can see this over here. So each branch is associated with a perceptron, okay? And a perceptron contains a set of weights, Wi, which are shown over here. Each weight corresponds to a bit in the global history register, okay? And it represents how much the bit is correlated with the direction of the branch, okay? So positive correlation, I don't know why this is going by itself. A positive correlation means if there's a positive correlation between the outcome of the branch, let's say taken, and the direction in that location in the branch history register, then you should have a large weight associated with it. And you, over multiple executions, you increase that weight by training, okay? And then if there's a negative correlation, meaning the outcome is taken, but the bit is not taken, or vice versa, this weight gets decremented over multiple iterations of training and execution. So that's represented by a large negative weight. So basically, over multiple iterations of execution, you can learn the correlations between the outcome of this branch and the bits in the global history register and encode those correlations in terms of weights. If there's no correlation, the weight would be 0, for example, right? And that branch, that particular bit will not affect the outcome as much. Okay, so what is prediction? Basically, how do you do the prediction? You express the global history register bits as 1 and -1, corresponding to taken and not taken. And then you take the dot product of the global history register and the weights. Remember, global history registers encode as ones and zeros, 1 meaning taken, 0 meaning not taken, which is what we discussed. And the weights are encoded with some value, so it's larger than 1 and 0. But if the output is greater than 0, you predict the branch as taken. Okay? I mean, this makes sense because output greater than 0 means that you're positively correlated with the taken outcomes more than you're correlated with the not taken outcomes, let's say. If the output is negative, then you predict the branch as not taken. And this is basically what this equation shows. There's also the bias over here, which this description doesn't talk about, but you can also set the bias bit for a given branch with some mechanisms. You can learn that bias bit, or you can set it in some other way, saying, okay, 99% of the time this branch was taken, so that bias bit is huge, right? That weight is huge. But you can also filter out some bias branches in different ways. So I'm not fully convinced about the usefulness of this bias bit if you actually have branch bias filtering, if you will. Okay, but this idea was introduced in 2001 with this paper, and you can read that paper if you're interested. There's just like in any machine learning method, there's a prediction function, which is this, and there's a training function, I'm not going to go into the details of the training function. There are multiple ways of doing this. But training is not as hard as you would do in a deep neural network today, which we're going to talk about in the next lecture somewhat. But this, you can think of this as a single layer network, right? It's a single layer network. It's a dot product essentially. There are no multiple layers. There's also, people have also developed multi-layer perceptrons, which resemble modern neural networks, except they're different in the training function, but they're not used in modern processors because they're much more expensive, if you will. But this is a relatively interesting area. Can use other machine learning algorithms and adapt them to hardware so that you can do this better. Okay, so I've already mentioned this bias weight, and this is the dot product of the global history register and the perceptron weights. Training function we're not going to talk about, and output is compared to 0. But now you can see this is the hardware costs. So you have a table of perceptrons, and you select the entry based on the branch address. That gives you the correlations of that particular branch at that particular PC with the global history register entries. And using the selected perceptron, you multiply it with the history register and also take into account the bias. And then you make a prediction based on that dot product computation, which is much more expensive than what we've seen so far, right? Now we have a bunch of multiplications that you need to do to get to a prediction. How do you do that? Well, there are papers that are written to actually make that cheaper. Actually, it's more difficult to do that in a cheaper, in a latency critical way. Okay, let's talk about the advantages. You have a more sophisticated learning mechanism, so you get better accuracy. It enables long branch history lengths, actually. This is better accuracy also, because now you don't use the global history register to index into a huge table. You use the program counter to get a global history, and your global history can be very long in this particular case. This advantage will be there in the Tage predictor that we will see also. But of course, complexity is a disadvantage. You have an adder tree to compute the perceptron output. It has some limitations in terms of what it can learn, and this is very well known in the machine learning literature. It cannot learn XOR functions, for example, like linearly separable functions, linearly non-separable functions. It cannot learn XOR type of correlation between two history bits and branch outcome. But later works actually tried to solve that. But this is one successful example of the use of machine learning in actually hardware today. So this paper describes how it's done in the Samsung SoC Exynos CPU. You can take a look at it. It actually also includes one of the ideas that we developed for indirect branch predictor. I like this processor. It has multiple different ideas. And then AMD has been using it actually for a long time, starting from the pile driver architecture to Zen and Zen 2. They employ a perceptron branch predictor. And this is their picture. Well, this is one picture that talks about an AMD processor. It's not an official AMD picture, but you can see it's very similar to what I just described. Now, let me give you another idea. This is the Tage idea, which is the competitor, if you will. And the idea here is to use multiple history lengths. And I've already given you the observation. Different branches require different history lengths for better prediction accuracy because the branch that you're correlated with may be either close or very far in the program, right? And it makes sense if you think about how you write a program. You may actually test a condition here. 1,000 instructions later, or I don't know, 1 million instructions later, you may test the same condition again, right? So there could be a correlation or a similar condition. And the idea here is to have multiple pattern history tables indexed with global history registers with different history lengths and intelligently allocate pattern history tables entries to different branches. So it looks like this basically. So you have 5 tables in this particular case. There's a base, very simple predictor. And then there's another predictor with a short history length. Here, there's no history length. As you can see, it's based on program counter. Here, there's some history length. There's a longer history length, longer history length, longer history length. And then you basically index all of the predictors and decide which one provides you the better prediction for a given branch. It's expensive, and this paper describes it. And basically, these folks say that increasing history lengths in a geometric series makes sense. Okay, and this is from something. I'm not going to go into the details of this, but basically you use different history lengths for different branches based on the predictability behavior. So the advantage is you can choose the best history length to predict each branch, better accuracy. Enables long branch history lengths. This is also better accuracy. So it's similar in terms of compared to the perceptron, but it enables different history lengths in very different ways, right? Here, we still use history lengths to index into the tables, whereas in perceptron doesn't do that. Perceptron indexes into a table and get the history for a particular branch. Of course, this also has disadvantages. Hardware design complexity is not low. There are a lot of things that you need to optimize here. And you need to choose good hash functions and table sizes to maximize accuracy and minimize latency. And people have done a lot of research in this. But this is also another successful recent idea that's used in many modern processor designs. Some processor designs admit it. For example, AMD's N2 employs both perceptron and Tage. They use a hierarchy of predictors, actually. At the first level, they use a perceptron predictor, and they have some confidence mechanism. If the perceptron predictor doesn't provide high confidence, they use a Tage predictor to overwrite that prediction because they have a long enough pipeline. They say, if I made a mistake in my prediction, I'm going to repredict this branch because I have a long enough pipeline, so I should fix my prediction. Sounds good, right? So now you can see the sophistication of branch prediction. The question is, of course, can we always do better, right? And I'm not going to go into the details of this, but modern branch, people have been proposing a lot of branch prediction mechanisms. This is one example with Tage. You have the Tage predictor, and then you get a confidence estimation, and then you have some statistical correction mechanism. And then there are multiple different predictors that you use to decide on the predictor. But basically, it's sophisticated. And there is room for other algorithms over here, as you can see. Okay, let me talk about confidence estimation, because this is, I think, something that I've been kind of throwing without talking about what it really is. This is really, and the idea is really to estimate if the prediction is likely to be correct. And this actually has many, many different applications. Estimate how confident you are in a particular prediction that you make. So why is this good? It could be very useful in deciding how to speculate, meaning what predictor, pattern history table, or other table to use, whether to keep fetching on this path or stall the fetch, because you may be on the wrong path, right? Whether to switch to some other way of handling the branch, right? If you have that option, and who knows what else. So the idea is to keep a record of the correct and incorrect outcomes for the past instance of the branch. And based on the correct and incorrect patterns, guess if the current prediction will be likely correct or incorrect. So basically, keep track of how you're doing in your predictions. And it can customize to the branch predictor also. Again, I'm not going to talk about the details of it, but the idea is different from branch prediction. You have a branch prediction, you estimate how likely you are to be correct in that branch prediction. So one example application is pipeline gating. This is a very simple paper in the past. It's a very simple pipeline. But basically, if you have more than some threshold number of branches that you're not confident on, that is in the pipeline, stop fetching. That's the idea over here. Very simple idea, because you're likely on the incorrect path. An incorrect path is likely to be energy inefficient or useless or harmful in terms of performance. Another idea could be to switch to another thread, right? If you're non-confident in your branch prediction. Okay, so I think I've covered what I really wanted to cover. What I'm not going to cover is delayed branching. I wanted to, maybe actually I will take a minute to cover this. Are people interested in this? Okay, so I'll take a minute to cover this. You may, if people have to leave, you can start leaving. But I will take a minute because this is something that I said is a bad idea, if you remember. And it's a bad idea, it's still a bad idea. I haven't changed my mind. Now let me tell you why this is a bad idea. The idea in delayed branching is to change the semantics of a branch instruction. We're not talking about branch prediction anymore. And the idea is to branch after n instructions. So basically, you change the semantics. The branch says, don't branch right away, branch after n instructions. So the next n instructions should also be executed. You could also say n cycles, but cycles are worse than instructions. So delay the execution of a branch. N instructions that come after the branch are always executed regardless of the branch direction. So of course, there's a question, how do you find instructions to fill the delay slots? So these are called delay slots. Branch must be independent of the delay slot instructions. So if you have an unconditional branch, it's easier to find the instructions to fill the delay slot. But if you have a conditional branch, condition computation should not depend on the instruction in the delay slot clearly. So it's difficult to fill the delay slot. Now, let me give you why this may work. So let's assume that you have a two-stage pipeline, fetch and execute. And let's assume that this is your normal code. So you have a branch from A to C, and then C to branch. These are dependencies, basically. You have a branch conditional that goes to X, okay? So this is linear code. This is C is dependent on A, and branches depend on C. And the rest is sequential code. So branch conditional skips all of these instructions, D, E, F. So if you're in this machine, you fill the pipeline. When you get to the branch, you stall the machine or predict the branch. Let's assume that you're in an old times where you're not predicting the branch, you're stalling the machine, right? You figure out the target when the branch conditional is executed, and then it becomes G. It's 6 cycles. Now, if you have a delayed branch code, you redefine the branch as the next instruction is always executed, okay? So you take this B that's independent, that doesn't lead to the branch computation, that's going to be executed. you take it and put it under a branch conditional. You don't change the semantics of the code, right? Because this branch B should be executed regardless, so you're always executing this. That's good. Now you fill the delay slot with a useful instruction, and you can reduce the execution time, as you can see, 5 cycles. So you need to be able to fill the delay slot. If the delay slot is 1 cycle, that's, in this case, we filled it. Does this make sense? Okay, so this doesn't always work. That's why people introduce the idea of delayed branch with squashing, and it's used in Spark ISA. If the branch falls through, in other words, it's not taken, the delay start instruction is not executed. Let's take a look at this. This is our normal code, simplified a little bit. Now you have all instructions dependent over here. It feeds to the branch computation, and branch goes back to the loop. So it's a loop branch. If you have just delayed branch, just like we described, you cannot fill the delay slot. If you cannot fill the delay slot, you put a no op into it, right? Which means that you basically didn't do any good to the machine. Now, if you have squashing, you can take the instruction that's in the next iteration and put it after the branch. And if the branch is taken, you execute this instruction. If the branch is not taken, you need to squash this. So this is a branch delay slot, but you have squashing. This helps a little bit, clearly. But now it's resembling branch prediction also, right? So basically, delayed branching can keep the pipeline full with useful instructions in a simple way, assuming that the number of delay slots is equal to the number of instructions to keep the pipeline full before the branch resolves. And all delay slots can be filled with useful instructions. Both are very difficult to do. So not easy to fill the delay slots, even with a 2-stage pipeline. Now imagine a 20-stage pipeline today. So people baked this into the ISA 40 years ago. They put 1 cycle delay slot. Hard to fill it. Okay, maybe you redefine your ISA over time, 20 cycle delay slot. How are you going to fill that, first of all? Basically, number of delay slots increase with pipeline depth, superscale execution width, and raised with variable latency. Okay, ignore that. The biggest reason why this is a very bad idea is it ties the ISA semantics with a hardware implementation. These people envision that, okay, you're going to have a 2-stage pipeline, or the branches will be resolved after 1 cycle. So let's have a delay slot, and the compiler will fill this delay slot, and we're not going to have branch prediction in the machine. Now you're tying your vision of hardware should be to the semantics of the ISA, and the remaining 40 years of your ISA's lifetime, everybody needs to deal with your delay slot. That's the story of MIPS delay slot, as well as Spark delay slot with squashing. These are essentially useless instructions, I would argue, in those ISAs, but they make the compiler designers' life hard. They make the hardware designers' life hard, and with no benefit, essentially, in today's machines. So I'm not going to talk about this since we're already out of time, but you can learn more about this in the static instruction scheduling lectures. Okay, so I wanted to cover this because there are some bad ideas, as you can see. Even though they have good trade-offs, you really don't want to tie some ISA semantics to the hardware implementation, as you saw. Okay, with this, we're done with branch prediction. Next week, we're going to cover part of this stuff, which is static instruction scheduling, and at least motivate why this is important by looking at the VLIW architectures and talk about systolic arrays. So have a great weekend, and I'll see you next Thursday.